Hi there, welcome to Calculus of Variations. This is video number 15. In this video I'm going to look at the first and second order variation of our simple functional which we've been dealing with over the last few videos. Now, as a motivation, let's look at a single variable example. If we had a coordinate axis, and we'll call that y, and we'll call that x, and we have some function f in that system, and let's take a point on the curve, we'll call that x, and a point up the curve, we'll call that x plus epsilon. Then this x will be a function, and the value there will be f of x. The value of this here will be f of x plus epsilon. So if we look at f of x plus epsilon minus f of x, we're looking at this height here minus this height here, which is this height here. Now if we take that across here, we would have that height there. Now we could make an approximation to that using the Taylor polynomial approximations. Now, I've already done a video in the snippet section on where I derived Taylor's polynomial and also worked through a little bit of what we're doing here now. So if you're not unsure about this, you could go over and have a look at one of those videos. Okay. So you could have a first order approximation, epsilon f derivative of x, and a second order approximation, epsilon squared upon 2 factorial f double derivative of x plus all the higher order terms, which get smaller and smaller, epsilon cubed. Now you can see roughly where this comes from. If you were to take the rate of change of the function there at that point, f derivative of x, multiply it by epsilon, then it would be equivalent to taking the gradient at that point. There we go. Multiplying the gradient by epsilon, and you would get this small height here. Now that would be a first order approximation to that height. That section there would be an error. Now if you wanted to, you could do not a linear approximation but a non-linear approximation, and we use a family of curves for the Taylor expansion called the Monomial Curves, which are curves of the form x to the n. So in this instance we make n2, then we would have a curve x squared. So we'd find the second derivative at that point there. Okay, and the curve would come up and along that way, and it would hug closer to the curve that we're trying to approximate. And again, the error would be decreased because we would have an extra bit of height there, but there would still be a small error. Okay, now the factor epsilon squared and 2 factorial, if you go to the video in the snippets, you'll see exactly where that comes from. So that's what we've done that there for a simple example there as a motivation. But what we want to do is we want to do the same thing for our functional. Now the functional that we were using was, if we give it a capital F, that would be f of x, y, y derivative. Okay, now that there would be similar to a simple function, be similar to the value here. Okay, now if we add on a small variation, in this instance here the small variation was epsilon, but this is a functional, so the small variation, if we write this as f of x, I'll rewrite that, I need that to be a capital, x, capital Y derivative. Okay, then we could then say that there would be equal epsilon times some value plus epsilon squared upon 2 factorial times another value plus all our higher order terms. Now we've got to find out what these values are. Now if you remember from what we've done in previous videos, we found our value y, large Y, equals small y of x plus epsilon eta of x, and our value y derivative equals y derivative of x times epsilon eta derivative of x. So we'd be varying our function there by a value of a family of curves eta x, and the magnitude of the variation would be determined by this value of epsilon. So if we were to then find be dy by d epsilon, so we differentiate that with respect to epsilon, we get eta, just our eta. Okay, and if we differentiate it again, differentiate this one here with respect to x, we get our eta derivative. Again, that we've done that previously, that's been done in other videos. I just put it in just as a reminder. Okay, so now we're going to look at some functional I as a function of x, y, y derivative, and we're going to look at di by d epsilon. Okay, so that's how we find this first section in here. Now, so what we want to do is differentiate the functional with respect to y and y derivative. Okay, right, we have to, so we want to differentiate the functional with respect to epsilon, but the functional has two terms that are dependent on epsilon, that is y and y derivative. Okay, x is not dependent on epsilon, so in order to do that we just use the a chain rule for differentiation. So we'll have partial f by partial y times the chain rule for differentiation, partial y by partial epsilon, and then we've got to differentiate y derivative with respect to epsilon, so partial f by partial y derivative times partial y derivative by partial epsilon. Now we already know that partial y by partial epsilon equals our value eta, and that there would be eta derivative, so that can be written as partial f by partial y times eta plus partial f upon partial y derivative times eta derivative. Okay, so that there would be our first variational, so that there would go in that bracket there. Okay, so our first variational we were dealing with would be epsilon. Okay, so that's the first derivative of not that simple function, but the first derivative of our functional. Okay, now what we're going to do now is we're going to look at the second derivative, so we'll be looking at d squared I by d epsilon squared, and we're going to go through the same process. We would have to multiply, we would have to find the derivative with respect to y of something plus the derivative with respect to y derivative of something. Okay, now the somethings here is this equation there. Okay, so we're just differentiating that once to get that, and then differentiating it again. So we're going to differentiate this lot here again. So if we do the first bit here with respect to y, so I'll just put it down with respect to y, then you're going to have, yeah, that's one right, so you're going to have a mixture of the chain rule and the product rule. So you've got two functions here, okay, they're multiplied together, so let's say that's function u and that's v, then you would have u dv plus v du, which is the product rule for differentiation. So you would end up with two terms for this here and two terms for this, so you would end up with four terms here altogether, four terms here altogether. So when we do this whole thing, we're going to end up with 8 terms, okay, but 4 of the terms will disappear and one of the terms, 2 of the terms will combine, so we'll end up with 3 terms just at the end, okay. Plus we've also got to do the chain rule for differentiation as well, because we're differentiating with respect to epsilon, and f is a function of y and y is a function of epsilon, so we need to use the chain rule. So let's just get ahead with it. So we're going to have partial squared f upon, it'd be partial y times partial y, so it'd be partial y squared times the chain rule, which would be partial y by partial epsilon times our value eta, and then the next part of the product rule would be partial eta partial epsilon times partial f by partial y. Okay, so that's 2 of the terms here. Another 2 terms coming up, so it would be, we're going to now differentiate this section here, so it's going to be partial squared f upon partial y times partial y derivative, so that's a mixed derivative, times the value times the chain rule, so partial y upon partial epsilon times the value of eta derivative, and then finally we'll differentiate partial eta derivative by partial epsilon times partial f by partial y derivative. Now this value here, eta, is a function of x, okay, eta is a function of x, eta is not a function of epsilon, so we can get rid of that, okay. Exactly, and again, eta is not a function of epsilon, so we differentiate that, we just get 0. Okay, so we're going to end up with just 2 terms there, so we'll have partial squared f upon partial y squared times eta squared plus partial squared f upon partial y derivative, okay, times, and we've not actually noted this down, but this thing here, partial y by partial epsilon, when we differentiate that we get eta, okay, partial y by partial epsilon is eta, when you differentiate that there you get eta, okay. So again, we went through that in previous videos, so that'll be eta times eta is eta squared, and the same here, that would be partial y by partial epsilon is eta, so in this term here we would end up with eta times eta derivative, okay. So we could just call that, we'll call that 1 for the moment, okay. So that's 2 terms, okay. Now if we differentiate now with respect to y derivative, respect to y derivative, then we would have partial squared f upon partial y derivative times partial y, it's a mixed derivative, and then the chain rule, partial y derivative by partial epsilon times eta plus the second part of the differentiate that product rule, partial n upon partial epsilon partial f by partial y, and then the second part of it would be plus partial squared f by partial y derivative times y derivative, so it's y derivative squared times by the chain rule partial y derivative upon partial epsilon times our value which we've got eta. Okay, value, where I am, let's see, our value eta derivative. Okay, and let's see, that's partial squared f partial y, just to get this 1, 2, 3, that's correct. Okay, and then the final term we differentiate will be partial eta derivative upon partial epsilon and multiplying it by what's left over of the product rule, partial f upon partial y derivative. Now again, eta is not a function of epsilon, so that cancels. Eta is not a function of epsilon, so that cancels. So you're going to be left with two terms. You're going to have partial squared f partial y derivative partial y times, now when we differentiate that we get eta derivative, so that will be eta times eta derivative. Okay, and then we come across here, we're going to have partial squared f on partial y derivative squared, and when we differentiate that we'll have eta derivative again, so that will be eta derivative times eta derivative squared. Okay, so we'll call that 2. Right, okay, so we end up with 1, 2, 3, 4 terms, and 2 of the terms are going to add up, and you can see that there. That term there is the same as that term there. So we're going to end up with, if I can try and keep them on here, we're going to end up with partial squared f upon partial, now I'll do it capital letters, partial y squared, okay, which is from this term here, right, eta squared, so that's that term done. And we'll also get a term here, we'll put it to the end, partial squared f upon partial y derivative squared, okay, times, and that should be eta derivative squared, I missed out the derivative there, eta derivative, okay, I have got it further up in there, haven't I? Yeah, let's see, right, okay, let's see, eta derivative, yeah, let's see, right, okay, so that's okay, eta derivative squared. Now the two terms combine, this term here and this term here, and you'll just get 2 of them, so you're going to end up with 2 eta derivative times partial squared f upon partial y partial, oh, that's capital Y, partial y derivative. Now that's really what we've been looking for. Okay, now we know that as epsilon tends to 0 from our equations up here, as our value epsilon tends to 0, then y of x will tend to large y, or large y will tend to y of x. So we could write then as epsilon tends to 0, then large y will tend to small y. So you could write that out with just the small values of y. Okay, now that's the final version of that, and we'll move on and we'll look at the next time we'll look at will be the derivation of the Jacobi accessory equation. Okay, thank you for listening and goodbye.